We are doing the last part of linear programming, part 4, and we'll be discussing about um, sensitivity analysis. And I was in two minds what to do here because I could either show you just the output or I could explain the mathematics behind this. So this is what you will see. This is the first output for the variable cell, and then later you will have another output which you will get on Excel, known as the constraint, the sensitivity analysis for the constraints. So like I've said, I want to show what to do here. Either just explain those values without teaching the mathematics, but I do think the mathematics is important. So it's up to you. You might ignore certain bits in the clip here and go straight to the conclusions, or you can try to understand the mathematics. So let's start again. So what is sensitivity analysis? So let me just pull this up. All right. First of all, we want to do sensitivity analysis for the variable cell. Now, what it means here is you want to see if I have to start from beginning, the profit equation is here, and you want to see how much you can increase or decrease the profit. So if I've highlighted 30 here, so it means that I would like to know by how much I can increase the 30. 30 means the profit per unit for product capital letter X. One unit is obviously 1, and X will be the number of units. So 30 is constant here in the sense that we started the question by having in mind a £30 profit on product X. My mistake here, this should be small letter X and small letter Y. There you go. So this is how we started, and right, so we want to see how much it goes up or down for 30, and similarly we want to see how much the 100 goes up or down, but bear in mind that we want to keep the optimal solution at B. So whatever we want to do here, the optimal solution at B should not change. So that's what the sensitivity analysis for the constraint mean, and you can't do both together. You have to do them one at a time. All right, so this is what I've said here. We want to know the range of profit for item X. Right now the profit is £30 per unit, and similarly we want to find the range of profit for item Y. To do this, we have to keep profit for item X constant, and that should be Y, capital Y. Right, so this is what we want to do. Now one thing we discussed earlier is the gradient method 2, I think, where we can avoid the graph and we can just focus on gradients, and I think I should have it here somewhere. No, yeah, here. So this is the gradient of the profit line, and once I discover that it lies between these two numbers, which are the gradients of constraint assembly and finishing, I know these two must be the binding constraints, and the remaining one is the non-binding. And how do I find the coordinate? Is just by solving the assembly and the finishing these two simultaneously, and I would get the small x small y, which I can substitute in here to get the maximum profit. That's how it was done before. So now I want to know, by keeping these two constant, I want to know the range for the profit for item X first and then Y, and but remember we want to keep these two constant here because we want the solution to be between these two. The solution stays between these two. I want to keep these as binding constraint. Right, so what we should do here is let's start with the initially it was 30 here. Let's start with this. So let's assume that it's a number. Remember, I want to find the range here, and if I rearrange, I'm going to get this equation. Take your time and practice it. And now, instead of having 0.3 as the minus 0.3 of the gradient, I have a general number as such, and I want to find the range of value of a here. Right, remember a was 30 initially. Now I want to know the range it can take so that I still have b as the optimal solution. So remember, whatever happens, the gradient of the profit equation should lie between the the gradient of the two binding constraints. There you go. So if I solve now for a, I've tried one method. You have so many methods. So for example, I've multiplied by 100 throughout just to get rid of the 100 in the numerator. I end up with this. There's some negative sign here which I want to get rid of, so I multiply by -1. When you multiply by a negative number, the sign here changes. We can try this and take any arbitrary number and see, and rearranging it will give me this. So remember, initially a was 30, but a could take anything between 20 and 41.7, and I will still get the optimal solution staying at b. So that's how it is. So that's the 30 initially in my question, but it could take any number between 20 and 41.7 to give me the same answer. So 30 can be decreased by 10 and can be increased by 11.7 to give me the optimal solution and b. So that's what we have here. 30 can be, sorry, where am I? 30 can be decreased by 10 to give me 20, or can be increased by 11.7, hence 41.7, which I got here. Now that's the mathematics. I can do the same thing for for the 100. Initially that's what we have. Now let's just change it and put a letter b there, rearrange, and I would get this one. And again, this is my gradient, which really do not forget this. I want this to lie between the gradient of the two binding constraints, and I can simplify to find the range of b. So one method again is do the reciprocal, which means numerator goes to denominator and denominator goes to numerator. And when I do reciprocal, the sign changes, and I'll get this. And I can see some negatives here, so to get rid of the negative, well, that's simplifying the numbers here. To get rid of the negative, I multiply by -1. Again, the sign changes, and I get this. Multiply by 30 to get rid of the denominator here, and I end up with this range of b. So b was initially 100. It can increase by 50, or it can decrease by 28, which I do have here. So that's the mathematics behind it. Again, you might want to know what I just said in terms of calculation, in terms of what you see here, but do not forget the interpretation of this, or you have to try this anyway in the lab as Excel lab work. And what you need for the test is just interpretation of these numbers, these four numbers. So here we have the 30 and a pair of numbers, and here we have the 100 and a pair of numbers. So you want to read the PDF and see how it's been explained here. I'll let you read that yourself. So that's the first sensitivity analysis which we made on the variable cell. Right, that's the first type of sensitivity analysis we can make. Right, okay, I don't know if I'm I might have made a mistake. I said sensitivity analysis for the constraint earlier. I don't know. This is actually the sensitivity analysis on the variable cells, right? So the 30 and the 100 from the P equation. Again, that's small x here, and that's small y here, right? So that's it. That's for the first one. The second one now is slightly more complicated, but I do want to explain the mathematics behind it, and it is quite important. But again, once you get this on your Excel, what you need is interpretation. You might forget the mathematics that I will explain, don't worry. but just for the sake of, of explanation, I need to make sure that you understand the theory a little bit. So here is the analysis of the constraint. What it means here is I'm going to take the two, there you go, the two binding equations, and I'm going to ask myself one simple question. What if, sorry, this is for the, can't remember which one it is, that's for the assembly, and this one is for the finishing, right? And my question is, what if I was given 1 extra hour, 1 unit? How much more profit would I have made? That's the simple question, by keeping this one constant, by the way. Similarly, so whatever I just said is case 1. Case 2 it would be, what if I was given 1 extra hour in the finishing? By keeping this one constant, how much more profit I would have made? So what I can do is just a simultaneous equation. For the assembly, I'm going to increase by 1 unit, there you go, and this one stays constant, and I'm going to solve simultaneously, and I will get this answer. You should try this. I will get this answer, which I can then put in the profit equation, and it will give me a new profit. That's if I was given 1 extra hour for assembly by keeping finishing constant, right? So what it means here is, instead of having this initially, remember your table, I think I can show it to you somewhere here. I don't know where it is, so should be down. Yeah, so instead of having this as the answer, I would have uh, these coordinates as my optimum coordinate to give me the maximum profit, and that's the earlier profit. This is the new profit when I increase assembly allocated to me, the time allocated to me by 1 unit, by 1 hour. I would have made an extra profit of 3.85 per hour, right? That's what it is, and that's here, that's what we call the shadow price. So briefly to summarize, if I were to increase the constraint for the assembly by 1 unit, keeping the other binding constraint constant, I would make an extra profit of 3.85 pounds per hour. That's what it means. Similarly, I can do it for the finishing constraint, which is if I increase 800 to 801 by 1 hour, I was given 1 extra hour to work on the finishing. How much more profit could I have made? So again, solve simultaneously, I get this answer, substitute in the profit equation, and it will now give me a new profit. Compare that to the previous profit, yeah, this, and you will get the extra profit per hour that you can make if 1 extra hour was given to you for the finishing, right? So that would have been, for the finishing, that would have been £10.77 per hour. So question is, if you have to choose, if let's say the boss comes and tells you choose, well, not the boss coming and asking you to choose. I think if the boss will have to decide, if the boss has to decide where to give that extra hour, which one do you think he would have preferred? Well, answer is clearly here. He would have decided to give 1 extra hour in the finishing because it's going to get him more profit compared to this one, right? So that's the constraint sensitivity analysis for the, oh dear, for the constraint. And I was talking about this one and this number. There you go, 3.85, 10.77, which we got here. Now, look, simple question now. At some point, we can keep increasing. I mean, the boss can come and say, let's keep increasing by 1 hour, 2 hours, 3 hours, and so on and so forth, whether it's assembly or whether it's finishing. But common sense tells me something. If I keep increasing without paying attention, then at some point the gradient, remember how we got this as the optimum point. I can take this line, and move up, and it will touch B last. So if I keep moving, if I keep changing the right hand side to 801, 802, and so on, or 2401 to and so on, at some point this straight line will not hit this as the loss coordinate. So this tells me that I can increase, the boss can increase, because at the end of the day, the boss wants to make profit. But to what extent? To how far can it increase the time or decrease the time? So this will explain these here. So if I so basically the answer is in front of you. We can increase the 2400 allocated to me by this much. It will be something, you can do your calculation, 2581.81, or you can decrease it by 480 hours, which means 1920. That's for the assembly. Similarly, when we increase the what is it highlighted here, right? So we increased earlier 800 to 801, but to how far can we increase? We can increase it to 1000, an increase of 200, or we can decrease it by 125, hence you can decrease it till 675. So that's just interpretation of these numbers. Again, I thought I'll show you some mathematics here. So it's a bit tedious to explain. I'm not sure what I did here, but anyway, sorry, that's probably not it. Anyway, that's not it here. I think I did it. Yeah, I did it here, I suppose. Yeah. So this, sorry, you can ignore the dot point 2. This was the optimal X and Y with the optimal profit. The 2 here is because of the decimal places, so it was exactly actually 2400. Don't worry too much about the dot 2. So basically, it's just analyzing the graph here and to come up with the answer. Like I said, it's slightly tedious to explain. It's not part of the syllabus. All you have to do is understand the meaning of these two numbers and how it affects the initial 2400, and these two numbers, how it affects the initial 800. But if I have to explain, I'll let you read the text yourself here. So that's quite easy to understand, and you can pause the video, you can look at your booklet, and you will understand what's been happening. But like I said, if I have to explain, it will get slightly tedious. I just need your attention. But again, only if you feel that you need to know the mathematics, that's when it's going to make sense, right? So it all works out around this gradient, right? So um, um sorry, let me just see something here. Yeah, right. So remember how we got this gradient. We got it because it's the gradient. How did we got this coordinate? Actually, because it's between this gradient and that gradient. Now if I keep if this stops being the gradient, because I need to know where, to what extent can I take the 2400 by keeping B. So what if B stops being the optimal point? So it means that this line will not hit B as the loss coordinate, right? So it's a bit tough for me to explain because I can't move the line. But basically, what I can suggest is you take the two binding constraint equation, as you can see, 5x plus 12y for assembly and x plus 5y for finishing, right? And you consider, let's talk about the assembly first. So that's the assembly here, this line. So if this stops being the optimal coordinate, then it will hit either here, let's check it out, yeah, 0, 160. It will hit either here, where it stops being between the gradient of this line and that line. So this will be the point, and here and here. So the moment I start moving the 2400 value up and down, it will touch here and here now, right? So I can take these two coordinates, again you can solve simultaneously, and put in the equation of b, which is 5x plus 12y, and you will get the maximum and the minimum with these two coordinates, this one a and this one. You will get the maximum and minimum for the right hand side. So that's what I did here in terms of Excel. So I get this value and that value. Here there is a decrease from 2400, there is a decrease of 480, which is here, and an increase of 181.83, which is here. Now the 83 and 82 here is because of the number of decimal places. Don't worry too much about it. So slight discrepancy on the second decimal place, but that should be fine, don't worry. So this is how I got it. Similarly, where should I go? Yeah, similarly, I was discussing for this point now, for the assembly. Now remember the spraying department as well is a binding constraint. So for this to stop being not to stop, but to remember, the whole point is to see where it goes beyond beyond the, so spraying is what, beyond the 1200, to what extent does it go up and down. So you will see that let me just check it out at 300 and comma 35. So 300 comma 35, which is here, and at the 0 to 100, which is there. So at this point and this point would be the place where the red line will start touching instead of touching B. So again I've put I've put, ignore the dot one here, so I've put x plus 5y for the spraying, and these two coordinates here would give me, sorry, not the coordinates, but the maximum, the extent of the number of hours given to me. So clearly I was given 800 hours. I could have gone to 1000, hence an increase of 200, and a decrease of 125, which we got from here. So 800 minus this is 125. So that's basically the explanation, the mathematical explanation behind sensitivity analysis. Now, just to recap, you don't need to remember the mathematics I've just been speaking about. What you need to remember is, first of all, try this and get this output on Excel. So what you need to remember is to interpret. So this is the variable cell sensitivity analysis. It means the profit increase and decrease. It can, for the 30 it can go to 41.7 and go down to 20, and this one it can go to 150 and go down to 72. That was the first part. And again, try this in Excel and you should end up with this. And here you can explain these two. This is the profit, the extra profit per hour you would make if one extra hour in assembly is given to you. This is the profit per extra hour you would make if that extra hour has been given to you in the finishing. So you will get question on these two, and you will get question on these values here. So this one was on the right hand side of the binding assembly. You were given 2400 hours. To what extent can it go up? It can go up till 2400 plus 181. That's 2581.8. Or how far can it go down? It's 2400 minus 480 hours on the right hand side. Similarly, for the finishing constraint, binding constraint, you could 800 was given to you. You could have given 200 extra hours, that is 1000. 800 plus 200 is 1000. And or you could have given as less than as 675, that is decreased by 125 hours, and that would still give you the optimal solution. That's it. That's the end of linear programming. I would suggest that you practice your Excel. You interpret values. You will get this for the test. And any question, you can leave a comment or you can email me. You know my email, and I'll get back to you. But you need to practice this. These are the typical test questions. Thank you.